Hi, in this video, so welcome back to AP Physics CE&M Unit 3. This is the unit on electric circuits. So here we're going to look at current and the motion of charges. Okay, so remember in electrostatics that we defined voltage as work per unit charge. So some things that you need to, there are other important quantities used along to describe the features of a circuit. Okay, the first thing is going to be current. Current, which is abbreviated I, is defined as the rate at which charge will flow through a circuit. So in electrostatics, right, you look at that static portion, that's not moving. Now, they'll move inside the conductor to kind of get to where it needs to be, but we're talking about a flow, right? They're not flowing, okay? Now we're going to look at here in circuits, what happens when those electrons or that current or that charge begins to flow, right? So there's your difference between electrostatic movement and current movement, right? So it is defined as the rate at which charge flows through a circuit. So kind of instantaneously, it's dq dt. If you want to look at the average, just like we've been doing some, right, it's delta q over delta t. Now, conventional current is defined as the direction a positive charge carrier will travel. It seems unconventional, right? Because it's actually the electrons that are moving, which is the negative charge. But current, the way we describe current is how does that positive charge carrier travel? Okay. As we talk about this, the electrons or the charge carriers will be moving. So they're going to have what we call a drift velocity. Drift velocity is related to current in the equation I equals NE V sub D, which is your drift velocity, times A. Now let's define some of these variables here. So N is something that we call electron density. So it's electrons per cubic meter, okay? The E is simply the electric charge, that 1.6 times 10 to the negative 19th coulombs. V sub D, that's our drift velocity. A lot of times in questions, this is what you're going to be solving for. So you're going to be looking for how fast are those electrons moving. And A is the cross-sectional area that they're moving through. All right, if we're talking about in a wire, then it's going to be a circular cross-sectional area. It could be something at random by, using a rectangle, right, or a square. So that's just simply, right, the area. So circle, pi r squared, squared, side squared. Sorry about that. If it's a rectangular cross-sectional area, then it's base times height, length times width, however you know that. And then finally, current density. It's just simply a third way to describe a current in terms of electric field. And so this is going to be, the electric field is going to be rho times J, okay? And J is that current density. Rho is something we're going to talk about also in the next video, is this resistivity, right? And so basically it tells you how resistive the material is. Notice that it's measured in what we call ohm meters. So ohm meters. Ohm is the unit for resistance, which again we'll get into here in a couple videos. But that's the unit for resistance. This resistivity you'll see pop up again when we do talk about resistance, because it's going to be that number times the current, or excuse me, the resistance in a wire. E, we go back to our electric field. All right, so let's look at an example problem using this equation, right? So we're going to use this equation right here. And again, in the majority of the cases, you're going to solve for that drift velocity, okay? You may solve for I, But this N number, before we move into the equation, so N, again, is that electron density. And so to find that, you're going to use Avogadro's number times the density of the material divided by the atomic mass of the material. So this is atomic mass. You do have to be careful though, because atomic masses are usually given in grams per mole. You need this to be in kilograms per mole. This is the actual, this is not resistivity, this is the density of the material. And the N sub A is Avogadro's number. All right, that's 6.022 times 10 to the 23. It's like number of particles per mole. Okay, so let's look at an example. So the equations we're going to, like, if you want to really focus on here, this one is not given to you. The electron density equation is not given to you on the formula sheet. The current equation is, the two current equations are given to you. So dq dt and NEVD over A. You may have to kind of use those in unison because notice they're both equal to current. But in this example, we're going to use the drift velocity equation. All right, so here we have a copper wire 2 millimeters in diameter carrying 10 amps of current. If the density of the copper is 8.9 or 8,900 with an atomic mass of 63.5 grams per mole, there's 1 electron per atom. Calculate the number of electrons per volume, which is our N value, and then the drift velocity of the electrons. Okay, so part A. So N, that electron density, is going to be equal to Avogadro's number times the density of the material divided by our atomic mass. Okay, but remember, we need this in kilograms per mole. So our atomic mass is going to be 0.0635 kilograms per mole. Avogadro's number, 6.022 times 10 to the 23. And our density is going to be 8,900 or 8.9 times 10 to the 3 kilograms per cubic meter. So now all we got to do is plug the numbers in. 6.022 times 10 to the 23 times 8,900 divided by 0.0635, right? So this should be a fairly big number. So 6.022 10 times 10 to the 23 times 8,900 divided by 0.0635, and we get 8.44 or 8.4 times 10 to the 28th electrons per cubic meter. Okay, so that's our N value. That's what we're going to use in our drift velocity equation, which is going to be, so part B, I equals NE V sub D times A. Okay, and so we're going to solve this for V sub D. So I equals NE A. Now we can, so this A, right, that's our cross-sectional area, not our not atomic mass unit. Okay, so that's going to be 10 amps divided by N, 8.4 times 10 to the 28th, E, 1.6 times 10 to the negative 19th, and then we're going to do our cross-sectional area, so pi times 0.01, because they give us a diameter. We need to cut that in half, right, to give us a radius. So we're going to say 10 divided by 8.4 times 10 to the 28th times 1.6 times 10 to the negative 19 times pi times 0.001 squared. And we get a drift velocity, right? So how fast these electrons are moving, of 2.4 times 10 to the negative 4th meters per second. So they're not moving very fast, right? Sorry about this. Hit the wrong button. So note they're not moving very fast, but they are moving, right? So that tells us that the electrons are flowing through our wire once we pass a current through it. Okay, so in the next video, we're going to continue work a little bit more, laying the groundwork for some of these terms, where we're going to look at such things as resistance, okay? And then we're going to continue working our way towards those concepts with the circuit.